with a group of us for years, and we are going to learn about the cutting-edge information on algae. I'm going to shut up and let him get started.
Thank you. Definitely, there's none of the conference organizers here that I can see, but I really appreciate the opportunity to speak, and this is a beautiful location, and I really appreciate this opportunity. As mentioned by Jason earlier today, this is the 6th conference I've been to. The 3rd I've had the luck of not having to organize a chapter. And I think this is actually, usually I give talks about looking forward, about specifically feedstock issues and advanced feedstocks. But I think I'd like to start this talk by actually looking back. It's been long enough that I can actually start to look back and maybe give some people some insights that know me, how I was inspired to get involved in this and kind of where I feel like I've come from and how it relates. Currently, I'm working on molecular biology of algae as a feedstock for biofuels, although I'm not representing the company I work for. I got interested in biofuels at a very young age and was really interested in completely replacing all petroleum-based fuel at some point. As we know very well, biodiesel, it's going to be difficult with biodiesel with vegetable oil feedstocks alone. But when I was first starting my undergraduate, I got this copy of Home Power magazine, and I'd been going to a lot of health and harmony fairs and that sort of thing in Northern California. And there was this, one of the articles, Brewing Biodiesel. And interestingly, Panama Bartholomew, apologies to Panama if I've never met him personally, he wrote this article. It's from Humboldt State University at that time. And he was actually influenced by Josh Tickell. So it's interesting, the Veggie Van organization influenced him to write this article about his forays into small-scale production of biodiesel. And when I read this article, I thought, hey, this doesn't look too hard at all. We can, you don't need a whole lot of like personal protective gear or anything, because biodiesel's safe. You can mix it up with the drill. And I don't need to go into detail. I'm not trying to say anything bad about the person who wrote this article or anything, but we all know that there's been issues with safety, that we've come a long ways, and I'm just trying to point out how far the community has come in small-scale biodiesel production.
Is that a propane burner under the thing?
And here we have a propane burner, as well as an outboard motor, an electric outboard motor used in the barrel to do the transesterification. Why wasn't I doing this, right? That's what I was thinking. And when you look at the parts list, it's like $668. You can get, as long as you can get a free hydrometer and a free propane tank, because that's on the donated list. In no time at all, you can be producing yourself fuel that you can just drop in ready to any diesel vehicle, ready to go. Again, at this point in time, we know that's not the case. Well, I finished up my undergraduate. I was really interested in that time. I knew some people that were making biodiesel. And I finished up my undergraduate at UC Davis and studied plant biology, thinking about future feedstocks and how we could provide a feedstock supply that could really supplant all demand. And I went on to Colorado School of Mines in Golden, Colorado, because it was near the National Renewable Energy Lab, to work on algal biofuels. And it was there when I was living at a co-op in Boulder that I met John Bush. At that time, I started talking to John about, hey, let's build a biodiesel reactor. Well, he was actually just coming on the tail end of the dissolution of the Boulder Biofuels Co-op. And so I said, hey, I heard we could make a biodiesel reactor for a few $100, and there's this thing called an apple seed. You just get an old hot water heater. I pulled one out of a building that was being deconstructed on the campus. I said, all we need is a pump from Harbor Freight, and we can be on our way, right? He was like, forget about it. I don't want to. You don't know what you're doing, and I don't know what this is going to be like. But I continued to persist. He'd come over for dinners at the co-op, and I continued to persist and ask questions about how we could do this and that. And he's a talker, so he's willing to share information, but he's still a little wary. And eventually we got a small grant to get some students and engineers at the School of Mines to build a trailer-mounted reactor. This wasn't the first trailer. The first trailer was kind of a joke. But we went to Harbor Freight, we got a trailer, and this actually is the recycled water heater from taken out of the building. And eventually he could see that I was really serious about this, and I didn't want to use an outboard motor, but I actually wanted to do some more advanced things. From looking at the info pop and looking at the forums, I wanted to do my own methanol distillation and back off the glycerol. This is actually a Coors keg taken locally, is locally produced in Golden. And it starts to do some cool things, you know, and before long we were actually producing fuel. I did have to replace an injector on my Jetta, admittedly, so it wasn't always it was never probably ASTM spec. But I learned a lot about the process, and one thing that we learned about is that there was a lot of misinformation just on the internet, and that it'd be useful to get people together in a forum to discuss the things that I'd gone through and challenges I'd gone through, and some of the co-op challenges John had gone through. And the trailer we produced eventually was actually used as an opportunity for training. John eventually, before he started his master's program, was able to use it for a lot of seminars, basically, on small-scale production and safely. And we, with the help of Mark and Graydon, started the collective biofuels. It was called the Liquid Biofuels.
You're the guy I should blame. I get it. Okay.
So at the time, it was actually interesting today. At the time, Maria Alvert said, you know, this should be the conference where we talk about what's the right pump to use. And it was really interesting. John giggled kind of during Jason's talk today because Jason was saying, you don't want to use a trash pump, you want to use a vacuum. But we're like, yeah, this is exactly the kind of conference. This is what, you know,
Success!
Finally got there.
We're talking about pumps.
And it was a good point because you don't want to emulsify all the particles. You know,
And by the way, I learned that at the local biodiesel conference from Steve TV.
Awesome. And we also have other representatives today from Omaha Biofuels Co-op. So we've developed a community, and I think it's really exciting, and I think it's great. So I hope that you don't all think that I'm just stuck in the lab thinking about pie in the sky ideas as we get into these further graphs. And I'm really excited about where this has come and where it can potentially go. So now to get into the down and dirty. So I'm going to go into why I think maybe food plants don't make enough fuel to make me happy. Vascular plants are great. They produce carbohydrates, which we can make into alcohols. Of course, that's a food source. Plant lipids we can use for vegetable oil or biodiesel or potential renewable diesel. So this is a paper from 1984, and I thought it was a really interesting graph. So what this is showing the total biomass productivity of a Dixie Runner or Early Bunch. What are these? I don't even remember the type of plant. It's like a pea or something like that. Okay. So the important part about it is that the total biomass produced over the course of these days after planting is relatively the same between the 1943 variety and the 1977 variety. What's different is actually the amount of energy that is going into the pod. So it's the same amount of light has been harvested and energy that has been harvested per square meter per plant, but it's more energy is being allocated. So the carbon allocation is going more to the pod, and that's just through traditional breeding and basically artificial selection. And that's happened over time because we have the resolution as humans to look at a plant and to taste it and see it and smell it and know that this plant is producing more weight and weigh it. And we have the resolution with higher plants through thousands and thousands of years to develop cultivars that we use in agriculture, which are far different from what would have originally we co-evolved with. In the same paper, it's kind of interesting. Unfortunately, you guys definitely can't see that. But you can see the scale of these graphs, and I'll just go through them. And basically, you have this as your total incident radiation. A huge amount of it is actually not absorbed at all and reflected. That's the biggest thing. There's a whole bunch that's missed by the leaves altogether in higher plants. There's some transmitted that goes through the leaves, and there's some that's unaffected. This last little one is not absorbed really. So you're left with this small little bar at the bottom out of that total light that's coming down through. And then if you magnify that back up, then there's a whole bunch of further losses. The amount that goes into catabolism, so just running the machinery to divide cells and things like that, the respiration. Removal from things. One thing that's not in here is insect herbivory, for instance. But at the very end, you're left with the grain, which is this. And that's kind of what I'm getting down to in terms of how much land do we need to produce the fuel that we would like to, if we were to completely eliminate fossil fuels, and how realistic is that possibility? And I don't mean just biodiesel, but all conversion of light in general into the fuel and the fixed carbon that we'd like to utilize. From that, even the fuel that we use, based on how we utilize it, is really important and something to think about. So this is actually from a paper that was just published a couple days ago by Stephen Chu, our own Department of Energy, the Department of Energy in Nature. And the fuel energy that goes into an engine you're going to lose a lot to cooling, exhaust, frictional losses, air drag, and eventually you're down to the Carnot efficiency, the actual energy that you're using to move the car and propel the vehicle. So I think all of this is important and can be optimized. And beyond the economic growth that we normally consider, efficiency is another way to grow in a sense. We have more energy just by being more efficient. So the take home from that, actually that should say 1984, Gifford et al. Paper in Science, was that the typical rate of the dry weight production per unit of seasonal for plants is approximately, for different plant species, about 3 grams per megajoule of light. I'll get into what that even means, how much is a megajoule, right? And the progressive increases in yield potential for wheat, barley, oats, and soybeans have not been associated with increases in crop biomass. So it's been increased with more of that carbon partitioning going to the crop. So in the case of corn, we have an increase in grains, and then the size of grains from teosinte, the ancestor. And over the history of the improvements, there's been this partitioning of this photosynthetic product into the rest of the plant, so that's the harvest index, and that's been the primary importance, not necessarily through improving photosynthetic efficiency. So, teosinte from 10,000 BC, when I'm down in Mexico, I've seen some of these growing alongside the roads. Few grains, and the grains are very small because that's what was evolutionarily driven. Over time, through selective processes, we've eventually gotten to flint and dent corns, which were then ultimately hybridized in the late 1700s, early 1800s to give modern F1 hybrids like the Pioneer hybrids you might see in the fields today. Corn is also a C4 plant, so it's able to fix carbon, so it's not limited the way other plants are by the amount of carbon dioxide in the air. So corn and sugarcane, these types of plants that have this carbon concentrating mechanisms, what makes them superior to some other plants in terms of just making lots of sugar. Now the question is can we do this with algae? Algae, we don't have the resolution to look down 10,000 years ago and see one algae or another algae and say, wow, this algae looks fatter and has more going on than this other individual algae cell. Now certain algae have been used, Arthrospira for instance, the filamentous algae, as a food source. But in general, we haven't been able to look at the vast diversity of algae and say, this alga is superior to the other, pick individuals out. So only in the last maybe 100 years at the most have we even really considered this as a possibility. So only in the last 30 years that we've been pushing really hard. There's really been kind of 3 main waves of interest in algal biofuels since the advent of biotechnology. And a lot of it's been concomitant to new technologies. When there's a new resolution based on genetic techniques or new resolution based on analytical techniques, that's kind of pushed new interest into some of these properties of algae which make them a potentially better fuel source or more efficient fuel source. In the case of the lab that I worked in grad school, we're looking at increasing lipids by knocking out a gene that allows the cell to make starch. So if it's not able to divert energy into starch, we're able to partition more into lipid. In actuality, the cell just more or less got sick. But one of the things you do a lot of times in the biotech world is you prove that you've knocked out the gene of interest by putting the gene back in and restoring the function. When we put the gene back in, it inadvertently put in additional copies, and the introduction of additional copies of that gene for starch production produced a cell that can actually overproduce starch. So relative to the wild type, it's basically similar to what we've seen with the teosinte. These are all starch granules packed into the cell, which you don't normally see under normal growth. Another consideration for higher plants is the lignocellulosic feedstock. And I think that's an important consideration beyond biofuels in terms of, I just want to drop into this for just a moment, which includes the crop residues like corn stover and sugarcane. That would definitely be the other part of the carbon partitioning and increase our overall efficiency if we can use that. And that's definitely something that's coming online now. It's very expensive. You have to use enzymes to degrade these long chains of sugars, basically. So the cellulase enzyme is able to go along the strands of cellulose and break them into individual monomers of sugar, which can then be fermented into ethanol. This could be much more efficient than currently what we're doing is turning starch granules, starch grain, into corn grain into ethanol, because you can use all these stalks and leaves which can't currently be used for animal feed or human feed. So there definitely gets away from that food versus fuel debate. But the cost of the enzyme has been until now very prohibitive, as well as pretreatment processes. You have to break up the complexity of the corn stover and leaves so that these enzymes can even get access in there. But there are basically large plants coming online. Unfortunately, they're all, because of the expense of this, kind of on a very grandiose scale. and still has not totally been proven. So one of the things I think about a lot is for the biofuels aspect, that, especially for the grassroots and small scale, is how much vegetable oil, animal fats, and total plant animal oils altogether are available. I apologize, this is a little bit old data, but it still kind of carries the point. It's not that different today than it was then. So what I basically did is I used this one source, and it's very similar to other sources I've looked at. You can see on the left hand is billions of gallons of production or consumption, either way. And a lot of times it's hard to look at these numbers individually. I'm trying to kind of present it in a way that's more digestible, because people say, well, how much of just diesel fuel, or how much of just on-road diesel fuel? And what I'm interested in is how much liquid fuel in petroleum are we using in this country, and how much land would that take, just all together, and how realistic is it to take that completely? So, and this is all the different kind of the military, on-road diesel, off-road, total diesel sales. And you can see that what we're looking at is a very small percentage from the oil that's being currently produced on farms, the current use of vegetable oils and animal fats. So that's not just for biodiesel, that's all animal fats, all vegetable oils. And so I calculated if we used all current U.S. farms and we converted them all to soy, so just in the hypothetical model, like all farmland that is being used for all crops and converted it just to soy, this is the amount that we'd be able to produce in terms of soy oil. If we did the same thing with canola, we'd produce that much. And so we'd basically only be able to get in the neighborhood of what's currently being used for on-road diesel, 100% on-road diesel. We'd have no food. We'd have no plastic. Yeah, exactly. So this is just an idea of scale. Obviously that's not what I'm proposing, but it gives you an idea of scale. Let's skip through these. So this is why I'm interested in microbial phototrophs. Unfortunately, I think there's a lot of interest in, there's a lot of sound reasoning on why we should be interested in microbial phototrophs, but I understand that they've been very oversold, especially since around 2007. From around 2007 to 2012, there's been large claims made from many companies about what can be done in a very short term. And I think that that's jaded a lot of people about the possibilities. So I'm going to just quickly go through what I think is the foundation for why there's an interest and where we're headed with it. So microbial phototrophs, algae, when I say microbial phototrophs, I'm not just saying algae, because algae are considered specifically, like us, having mitochondria. We don't have chloroplasts, but having intracellular membranes, basically, as opposed to cyanobacteria like Arthrospira, spirulina, which do not have any mitochondria or intracellular membranes or chloroplasts inside them. They're basically similar. They're a type of bacteria. So we have, those are kind of distinct in terms of microbial phototrophs being broken into those two groups. But in any case, the different classes, not all of them, but different classes can produce starch or similar glucose starch-like molecules, and as well as lipids. You can also induce them to produce alkanes, basically something very similar to what diesel is, just a straight carbon chain with hydrogens, and that's been done through genetic engineering and hydrogen, which is what I did a lot of my work on as a graduate student. But the main thing that people are interested in is this increased photon conversion efficiency. On the left side, you can see, for instance, under nitrogen starvation, when the cell's not able to divide, it's still doing photosynthesis, and it's putting that fixed carbon into stores of starch, which is kind of the white areas in the lower there, and big stores of lipid. On a huge scale, like in a giant pond, now that's really interesting, and in a flask you could say, oh, that's really efficient, we're producing a lot of starch and lipid. You multiply this by so many gallons to be an acre, that'd be great. You know, we can produce, as they said in the ASP, like 10,000 gallons per acre per year. But obviously, when you think about the actual mechanics of that, how are we going to limit the nitrogen? They're doing in the lab, they're centrifuging the cells down, they're resuspending in a medium without any nitrogen at all. So I'm interested in, the possibilities of really making this happen, and that's what I'm pursuing. There's been a number of reviews since the resurgence in interest in algal biofuels. This is one that's based, actually this data was originally presented in 1998 by Mike Seibert, who was at the National Renewable Energy Lab. And this is kind of an updated version. And so you can see the square in the very middle first is the 2006 corn crop. It's amazing that it's that big. And if you've ever been through Kansas or Nebraska, you know how much corn, even in California, in the Central Valley, there's a tremendous amount of corn being grown in the United States or flown over these areas. With the predicted conversion efficiency for cellulosic ethanol, you could basically take all of the cellulosic ethanol. Now, about 10% needs to be tilled into the soil anyways to replace the carbon. But where I grew up in the Central Valley of California, there's huge burn piles every year in the fall. With a lot of that stover is basically being burned off. You can't feed it all to cattle. You can't till it all into the soil. So there's a great deal of that that could be made available as part of the silver buckshot kind of approach, and that's I think really important and interesting. But again, we're still dealing with the technological hurdles of actually processing it all the way to ethanol. If you were to use corn grain, you're all aware of corn grain and subsidy for ethanol, and you're using it solely to replace U.S. gasoline requirements currently. It's this really large green square, so that's obviously not going to be an option. The efficiency is just not high enough. But on the left side is what's predicted, and it's been predicted at 1% efficiency. Basically, they'd say approximately 1,000 miles by 1,000 miles of 1%. I think this is based on a 3% efficiency, which is pretty normal for algae. So it's in the neighborhood of less than 500 by 500 miles. That's still a huge amount, but it's similar to what the 2006 corn crop, and that's with ungenetically modified algae that currently exists.
And that's land mass, is what that's what
This is land area, so you.
But I mean, but you can put the algae wherever you want, though, right? You
Yeah, you don't have to
desert.
just take over New Mexico. Yeah, you
Right.
you can distribute this anywhere.
But no, I meant that you don't have to displace farmland, or you can
Right.
unusable land that's not used.
Yeah,
now.
that's something I would have liked to get into more of, because if you talk to petroleum engineers, they'll tell you that there's a lot of untapped saltwater reservoirs that are near the petroleum reserves that are not used for agriculture, they're not obviously used for drinking water, that could totally be used for algae. Now, it comes to micronutrients, macronutrients that require nitrogen, phosphorus, potassium. That's where I think wastewater could play a huge role. And I think integrating algae into life cycles where these nutrients are put into a cycle as a means of both purifying the water as well as recapturing these nutrients for fertilizing purposes would be extremely useful. And that's one of the reasons we have a kill zone outside the mouth of the Mississippi is due to the nutrients which are causing algal blooms. So I think recapturing the phosphate that we're digging up as rock phosphate and putting on fields as fertilizer in the form of algae, and then using that as a fertilizer is one way that we can tie this into a cycle and have a value-added co-product. Yeah.
Could it actually help clean the boat?
That's exactly what I'm proposing, is that by co-localizing waste. Now the question is then, the land use, and that's something I'm not an expert in, is the places that people are typically looking are co-localizing these plants where there's carbon sources already, where we're already burning coal, can we recapture that carbon and have it obviously a lot of algae grow much better when you're actually treated with CO2, so can you co-localize in the Southwest these algae plants along with, but then that's not necessarily co-localized with the source of the eutrophication. So there's going to be some complex problems, but at the front end, the question I'm really addressing in this talk is, what is the actual potential of the algae? What I feel is a really conservative estimate for the production value of algae and how much fuel can we get out of that? So is there justification for moving forward with continuing to put energy, effort, resources into directing towards those problems?
I want to ask the difference between gasoline and diesel in this context.
Yeah.
And I know that some of these algae can make either gasoline or diesel, and I don't quite understand the difference. Can you kind of explain?
I've got a slide that actually has the chain links, and it'll totally go into that for sure. I think it might be coming right
And
now.
just to follow up real quick,
Yeah.
that's just gasoline.
So this is just a gasoline requirement. This is what I mentioned, that a lot of these studies will specifically say just on-road gasoline or on-road diesel, or but when you think about the entire picture, the real question is for me, is what's going to happen in 200 years when there's no more petroleum reserves? What mix of renewables is going to be required, and what kind of lifestyle, what kind of infrastructure should we be building right now in preparation for a peaceful habitation of this land in 200 years from now, and using the energy that we have wisely and the massive amount of resources and wealth that we have as a country right now, so that we prepare for somewhat selflessly, I guess, but I think it's logical to prepare for the time to come when petroleum is not available. So this is another study where they looked, and I'm sorry if it's a little small to read, where, and this is Jonathan Gressel, who's done a lot of algal cultivation in Israel, producing Dunaliella and whatnot for like nutrients, basically, nutritive purposes, which are very expensive products, and you can grow them at a high cost and still make a profit. And the basic bottom line is that maize, or corn, produces about 172 liters per hectare. So in order to, so the land needed basically to generate enough fuel, I believe this is for, I'm sorry I didn't actually write it down, to supplant our existing transportation fuel demand. In this case, is 462 million hectares, which is 178% of the existing U.S. corn crop. So that's similar to what the other study showed, is that you need more than is even reasonable. And actually, no, you know what? This is diesel, because these are all diesel options. I don't know why they have corn oil. That doesn't really make sense. But for these other oils, you can look it up too as well. But the main point is that there's different estimates based on the amount of oil that as a portion of the algae biomass as to how much land you would need. But comparatively, it's orders of magnitude greater production by this estimate. And you're looking at 1.3% of the U.S. crop area, or 0.6% is 70% oil of the U.S. land area using an algal crop. This doesn't take into account some of the things I'll cover shortly, but that's a very, I think, positive estimate in terms of how much.
It's motivating.
It is motivating, yeah, it's positive. And the question is there a consensus, though? Is this just one screwball, or is this something there's consensus? So another study done by Campos and Darzens. So Al Darzens was at DuPont. Before that, he was the head of the NRELS program in Algae Biofuels, and Campos is now the head of the Algae Biofuels. They've done the National Roadmap for Algae Biofuels a couple of years ago, and when it comes to reinvigorating the aquatic species program. And they have very similar estimates. The way it's really difficult to interpret this data, again, because it's presented in such different ways. But when you look at soybeans, for instance, if you planted 63.6 million total acres, you plant 4.5% with petrodiesel. So this is like the 5% by 2012 kind of push, and that's at 48 gallons per acre, which I think 60 is the most I've ever heard. So I think it's a pretty reasonable estimate. And then they've looked at low or medium or high productivity algae. And I can't remember what they used for productivity. I think the productivity was somewhere between 40 and 60 grams per meter squared per day, which is it's high end, but fairly reasonable. It's not like crazy. And basically what they've said is that from that same amount of acreage, at 15% tag production, you're going to get basically the same amount of acreage which is predicted as being possible for this 5% goal for biodiesel. You could plant 61% of petrodiesel just by itself. And at the high end, at 50% tag, you're looking at 100% on tenfold less acreage, which would be amazing. And that's again diesel, and so diesel and gasoline going back. I'm just trying to get people a picture. I just have diesel. That's what I wanted to do, and I never got around to it. But diesel and gasoline are somewhat similar. They're not exact. If anyone knows, please step in.
The numbers?
Yeah, diesel and gasoline.
Gas is about 200 billion gallons. Diesel is about 65.
Okay, so it's more than twice. So
It's about triple.
okay, it's about triple. So we can do that calculation pretty simply. So if you're talking about, but still, if you're talking, it's hard when there's so many orders of magnitude being thrown around here, without thinking about all these other things. It's a difficult thing to look at. But I don't think 50% tag is unrealistic from my own experience of working with algae. I think 25% is more realistic for continuous culture. So let's look at the 25% tag production. So they're talking about 25 million acres. So you would need basically fourfold that to do 100%. If you're talking about diesel being a third of the total gasoline requirement. So it's still, I think, it's within a scale, it's starting to come into some sort of consensus that even unmodified algal strains are not like this unreasonable scale, and whereas land plants do seem to be on somewhat of an unreasonable scale to even come close to our current demand. Now in any case, increasing demand or considering growth or exporting and using a complete biofuels economy for fuel seems unreasonable. but it's going to be tough either way. Even in the best case scenario, it's going to be tough in the future to completely remove ourselves from petroleum fuel. But it's not like we're in, it's a dire situation where there's no option out there. I think microbial phototrophs do provide something that's very positive, which we should be looking at. Yeah, sure.
Do any of these numbers account for the inputs? Like I keep hearing that algae needs sugar. Like that's the latest buzz in the headline, I guess, is that all this algae, you got to pump it full of so much sugar.
Okay.
Get that from Argentina. Or
So thank you for asking that question, and that's a really important question. And the reason why I think that that's come from the media is because there's a company called Solazyme based out of San Francisco, and they're using cane sugar to feed to algae, which are grown in big fermenters, which can produce almost basic directly biofuel equivalents. They're also producing skincare products as well. They're more value added. The reason this came about is because there's a company in Boulder, Colorado called Martech, which makes nutritional supplements, omega fatty acids from algae. And they can feed it sugars. That's a very expensive product, and they can sell it at very high profit, and it makes sense to use sugarcane or corn sugar to feed that and sell these as very valuable. And they're basically one of the only companies that sells algal-based nutritional oils, and they don't carry with them some of the contaminants that people have concerns about in fish oil. And so they've made a market. They've also found a market in baby formula as well. They added to baby formula for brain health as well. So Solazyme has gone out after that model, which has already been proven, as a means to be the first to actually show barrels of algal oil. They could produce barrels of algal oil. They can put it in a jet. They can do publicity stunts. And that is a way to get a leg up. They're also a publicly traded company now, so you can see why there would be a benefit to have barrels of oil in a warehouse to be able to show that as a publicly traded company. And when they opened, their stock was pretty high. It's kind of taken a dump since then, as people realized what this all. People are smart enough to put two and two together, but it has created confusion. The ultimate goal is to take CO2 from the air and make the sugar itself. You lose these efficiencies if you're going to use corn or sugar cane to produce the sugar, and you're going to convert it with an alga. You might as well convert it with a bacteria. A bacteria converts sugar into anything you want at about 85 to 95% efficiency. You can just forget about algae altogether at that point. And that is something that's been proposed, especially using specifically solar panels, to actually couple solar panels directly to bacteria that can fix CO2. And that's a recent paper in Science, actually, by Jim Liao from UCLA. It says that, well, solar panels are 10% efficient. We can do this conversion at 30% efficiency of that, so you're down to 3% efficiency directly to fuel from solar panels. And when he gave a presentation recently, I asked him, but what about the metals that are used in the solar panels? Have you done a life cycle analysis on hundreds of miles by 100 miles of solar panels? Plus the solar panels required. Should I start investing in these rare earth metals right now and make that my 401k? Because there's a limited supply there too. So I think it's important to think about the whole thing. But it's good that all these technologies will be investigated for sure. But I think, yeah, you're right. Sugars, converting plant sugars to fuels by algae is not going to be a scenario that anyone's going to propose as a long-term solution. There's another question? I tend to go through these too fast, actually, so I should probably slow it down. So as I was mentioning, they can take CO2 from the air, and they can produce carbohydrates, which can be converted into ethanol or butanol. They can produce lipids, which can be used as a diesel surrogate. Surrogated, that's a typo. So when I say diesel surrogate, I mean you can actually convert it to biodiesel, but if it makes more sense, you can make renewable diesel. And it's something I'm very interested in, whether renewable diesel could someday be a grassroots endeavor. And I don't think it's that crazy to propose that. It could even be safer than biodiesel production. And another option is proteins, and so proteins will also be produced just naturally because they're required for life, and those can be used for animals feed and methane. So I think it's going to be really interesting to see how algae can not only be used for these co-products, but also can be used to clean up wastewaters, and how the co-products can be used as value added to make the supply chain.
So do you have any hands-on experience of actually having the algae and then producing oil producing biodiesel from it, or
diesel surrogate?
yeah, the new, what do you call it, recycled, renewable
Yeah, renewable fuel.
Can you speak?
No, I know. We definitely, I definitely have experience with quantitating analytically, quantitating the amount of oil in the algae. But in terms of the conversion, that is something that I know is going on. I've seen proof of it myself, but I've not been involved personally in that.
Omaha Biofuels Co-op board member Scott Williams is currently working in a postdoc position at Johns Hopkins, taking algae grown by their company who got an SBIR grant and doing oil extraction, and it's developing quickly, so I hope to have more updates in the future. If you have more questions, we can talk a little bit about that. But I do have a little vial of oil algae at home that was grown at Johns Hopkins. It's very exciting when he sent it to me.
So, but the algae that we are growing is it's really normal for algae. It's not strange at all to accumulate up to 40 grams. Actually, I'll get to that. But around 20 to 40 grams per day per meter squared is not unreasonable, and it's not unreasonable for that to be 10 to 50% lipid content. So the numbers are there. It's not a pie in the sky. Other questions?
Current algae strains, and I know you're working on bioengineering. What's the ratio of carbohydrates, lipids, and proteins?
Is completely variable. I actually thought about that when I was making this slide. Like, which one should I present? Like, how should I adjust this? And it's the proteins are generally smaller than carbohydrates and lipids. The lipids are actually broken into two different types. There's the storage lipids, and eukaryotic algae are triglycerides, just like in seed oil. But there's also the membrane lipids, and those are all extremely variable depending on the growth conditions and the strain. There's some algae out there that are actually more evolutionarily related to you or I than they are to other algae, given that they've actually taken up their machinery, photosynthetic machinery, for much further along, we believe to be taken up much further along in evolution than the algae that are closely related to plants. So some of them are very, very distinctly different and only share some of the most basic parts of photosynthesis. So it's hard to make generalizations, actually, because of they're so different, such diversity. That's why when I got into this, actually, I thought that there must be strains out there in nature that are already going to meet our requirements for production. So in terms of what you can do with these things, so this is also from that recent Nature paper from just a couple days ago from Stephen Chu, is there's a number of different ways to go through this. And I just recently went to a Biofuels, Bioproducts, and Biorefining conference that was held in San Diego. And there was really a testament to human ingenuity, all the different ways that people are converting the biomass that's produced. I'm mostly interested in how to produce the biomass most efficiently because that comes down to the footprint, the amount of land you're actually going to require, and whether that's realistic. Now, other people even proposed putting ponds in the ocean. The Omega system is an example of that, where they were talking about actually having ponds in the ocean, and the birds would hook them in it and so forth. But people are trying lots of things based on the premise that it's efficient, and I think that's that is the foundation of trying these other things. So on the top, for instance, is using cellulosic sugars. So if you have cellulose and things like that, you have to hydrolyze the cellulose into individual sugars and ferment them. You can also do pyrolysis or syngas production, so you actually break it down into very simple gases and then rebuild it by Fischer-Tropsch synthesis into exactly the carbon chain length that you want to produce. Or you can do traditional transesterification, this last year, or catalytic upgrading to basic biodiesel or renewable diesel, so-called renewable diesel. And you can end up with a number of different things from the biofuels that you're producing, ethanol, methanol, butanol, alkenes, aromatics, and ultimately, hopefully, all of the necessary building blocks for all the things that we enjoy that are currently produced from petroleum. So going back to the strain that we worked with where we overproduced the starch strain, you can just see normally under the deprivation of nitrogen, as I showed before, that it can overaccumulate lipid and starch. Our strain with the overexpression of this isoamylase gene does it naturally, just under normal conditions, which in an open pond would be great. And this is one of the reasons why I'm an advocate of at least exploring the potential of genetic engineering. I know it's kind of a bad word in a lot of crowds. My analogy for it is electricity. You can use electricity to run an artificial heart during a heart surgery. You can use electricity to run an electric chair. It's totally how you use it. And I think that it is an extremely powerful tool. But I've also seen the possibilities for some really good things to come out of it. It definitely needs to be regulated, but it's amazing what we could possibly do and speed up the process of what we haven't been able to do over thousands of years of selective breeding.
How long do you think it'll be before Monsanto gets involved in this, if they're not already?
I don't know why they wouldn't. But that's that's the kind of the politics of it versus. It's definitely an important discussion. There's the political side of it, as well as just whether or not it in and of itself is a bad thing or a good thing. And I think it's incumbent on us to have these kinds of discourse and discuss and how we want to implement it if it's considered, first of all, whether or not it's a useful tool, whether it should be used, and then discourse about how, as a democratic society, we want to see it being used. And that goes back to the kind of the movie we watched last night. But to me, they're independent but interlaced issues.
What effect can the genetically modified algae have on the non-genetically modified algae? Like, can they crossbreed and
So
take over? Is it aggressive?
Yeah.
They fight.
that's an open-ended question. I couldn't make a generalization about that. In this case, these algae are grown only in the laboratory environment. In the case of the company I work for, I can't say anything about it. I wish I could explain more about the studies we've done. But in general, there's a general feeling that when you've manipulated either an agricultural crop or others to be substantially putting more energy into producing something of value, they're not competitive with those in the natural environment.
Mm-hmm.
I wish that I was walking along the street and I saw more organic tomato plants just growing, or zucchini just popping up and competing with shrubbery along the side of the road. But unfortunately, they just don't make it in competition in the natural environment. It's not to say it couldn't happen. There are cases where that can happen. I think it's a valid concern. But that's, in terms of the community I work in, that's one of the main things they fall back on.
For the nitrogen deprivation, is that total nitrogen deprivation? And if so, how do you compensate for the reduction in biomass production?
So that's a good point, actually. So in the case of, that's one of the reasons nitrogen deprivation is not necessarily a good strategy for increasing yields, is that it's a transient effect in which the cells aren't necessarily, in this case of this species, the cells don't divide, they're just packing on biomass. So biomass is accumulating at a similar rate, but cell division is not occurring at the same rate. So that's why the nitrogen deprivation phenotype is not necessarily a realistic way to go about making a biofuel. In the case of the strain that is overexpressing the isoamylase gene, we see cell division continuing on in the presence of nitrogen, growth occurring, still producing protein. So we see some aspects of this phenotype, but the cells are still growing at quite a great rate. And I don't have the data in this presentation, I had it last year, but in terms of the biomass productivity per day, which is really what it comes down to, we get a much greater starch and biomass productivity per day.
You ever looked at CO2 uptake per acre if you had a really dense algae farm? I mean, that has to be significant.
So
just taking CO2 out of
so the CO2 uptake will be very similar because it's mostly carbon to the amount of biomass that's produced. So if you just measure the kilograms of biomass produced, some of that's obviously the nitrogen, phosphorus, potassium, but in the majority that is the CO2 that's being consumed. You can calculate it that way. We also in the lab, of course, calculate how much is lost and whatnot. You can actually measure it by pH because the pH shifts with the uptake of CO2. So if you need to add more CO2, the pH will become slightly more alkaline. Add CO2 and bring the pH to a slightly acidic by the bicarbonate in the medium. So it's definitely taking it up. So just keep it going. This is just some staining pictures that actually show the lipid and the starch accumulation in these strains that we're expressing. And the work's continuing on in the School of Mines looking at these strains. So Jason had also asked about the contribution for biodiesel or a diesel surrogate versus a gasoline engine surrogate. As you all well know, a diesel engine burns things like biodiesel or vegetable oil because it uses compression and ignition, whereas we use a spark ignition in a gasoline engine. And so smaller, lighter chains can be burned in a gasoline engine typically. I'm no expert on exactly the chain length. I believe it's like 8 to 12 or something like that would be something that might be used. Please speak up if anyone has more expertise in that. Whereas what we typically see in a biofuel that we use for like lipid that we use for biodiesel, we see longer chains. So we see things along 16 to 18 carbon. The reason there's multiple, this is a high pressure liquid chromatography chromatogram of these different types of oils. These are all standardized from an old instructor I had at UC Davis. And the reason you see different peaks for the same chain length is because of the different levels of saturation, the numbers of double bonds or single bonds that are in these, and these fames basically. So this isn't necessarily an example from an oil seed. But one of the things that you can do with synthetic biology is actually specifically change those lipid chain lengths that would be more appropriate for specific types of fuel. And a colleague of mine, Brando Radakovitz, has done just that. He introduced into feodactyl an enzyme called bioesterase. And what it did is it basically stopped the growth of a chain at C12. And so it produced a chain at C12, which would actually make a lighter biodiesel or a fuel more appropriate. In this case, it's just preliminary evidence. It's not necessarily a lot relative to predominant, which is the C16 and C18, which you typically would see in a plant seed as well. But it's something that can be modified and would probably make it less competitive in the environment. And it's not something that a lot of people are concerned about in the same way. Excuse me. As the Monsanto's concerns, where it's antibiotic resistance, things like that, herbicide resistance. It's a minor change in the type of oil that's being produced. And it's kind of subtle changes that can make a difference in the economics and make it a more valuable fuel, and also make it more directly processable into a viable fuel. So it's something I'll just touch on real briefly, kind of a little bit of a side note, is that one of the ways that we're measuring the productivity of algae is directly by the productivity of photosynthesis, because that was one of the things that got me into this in the first place. Is I saw this huge diversity of algae from a phylogenetic standpoint, and maybe 300,000 or more strains out there. How can we assess them really rapidly for their optimum productivity? And so I started a small company based on a technology that we developed and patented at the School of Mines. Basically, what it involves is it's a small chamber. It's a 1 milliliter chamber. You can stick 2 probes on either side, and these are platinum silver probes, and they react with molecular oxygen or hydrogen. In the case I was studying hydrogen production as well from algae. You can measure the oxygen produced when you shine light on the cells, and that oxygen is directly relative to the amount of carbon that's being fixed, the amount of electrons that are being moved through photosynthesis. So you take individual strains, you can modify the strains, and you can put them into this Clark electrode system and actually measure their effectiveness at photosynthesis, which will eventually hopefully apply to larger scale. This is now available off the shelf. The company, we just sold our first commercial unit to an Israel university, to a lab there, and we're hoping to continue to make cells of these to labs that can quickly screen through new strains or modified strains for productivity before going on to test the lipids and that sort of thing. That's kind of the whole unit from the side. So we built this completely by hand. It's got a National Instruments DAT card, our own circuit board that we had printed. We've soldered it all on. We developed the cooling system. It has basically a jacketed vessel, so we can keep the temperature constant because that affects the measurement. The LED is also cooled so that we can calibrate the light intensity. So we can step up the light intensity and measure oxygen production as we step up the light intensity to get a measure of how productive the algae are in different light conditions. Stirred vessel.
Come a long way.
Have you seen it?
Well, I remember last year when you first showed it.
Yeah. Yeah, so it's gone a long way, and we're starting to make cells and getting some interest in that because there are some other similar devices that aren't quite as automated. We're trying to make it easier for people to do the kind of work that we do. So, let's see how we're doing on time.
20 minutes.
20 minutes, okay. So, quickly I'll go through some of the cultivation methods that I've also shown last year. There's a lot to the whole process of producing algae, and this is, I think, where the devil is in the details. Mm-hmm. Okay, so we're getting down to amount of grams. I started to present grams per meter squared, and that's really interesting and everything, but how much energy is it going to take to separate the algae from the water? I think that's a really valid concern because basically there's more water than there is, grossly more water than there is algae. There's maybe 40 grams a meter squared, but you might have 50 liters in that same meter squared. So the idea is that initially there'll be a CO2 source, so this will be co-localized with existing CO2 sources like coal production plants. You'll cultivate it, the oxygen will be released. It's unlikely, I think, that would be harvested as a co-product. And you'll have to harvest and de-water and recycle the water, mix it with a source of nutrients. Ideally, these nutrients would be wastewater, eutrophied water off of agriculture, or ideally, for me, I think it would be interesting to incorporate it into basic human wastewater. processing eventually is going to have to be split into different types, lipids, protein, and dry biomass, which can then be used as well for fertilizer. That picture didn't come up. Oh, there it is. So this is a classic raceway pond. It's the most inexpensive way you can grow algae. You just have a large raceway with a paddle wheel, basically, that can turn around. It's very inexpensive, but it's very open to contamination. It could also be open to concerns of the algae escaping as well, so you have concerns about that. Typically, CO2 would be bubbled into a pond like this, and it's just grown as this. And these are currently being used already, especially in Israel and as well in the Southwest.
In the Raceway setup, how are they dealing with bloom and crash cycles? Are they having a problem with that?
Oh yeah, it can definitely happen, and definitely other strains which are more opportunistic to that environment, as well as things that eat the algae can come in, so they have to be cleaned out, and that's another technology. As this is a kind of a new form of agriculture, there's going to have to be a lot of new sub-technologies that will have to be developed to deal with the problems that come about. The reason it's worked so far in places like Cyanotech, Rice Farms, is because they're selling a very valuable product. When you're selling a nutraceutical that's worth tens of dollars per kilogram or hundreds of dollars per kilogram versus single dollars per kilogram, you have the ability to get in there and use a lot of man hours, a lot of labor, and do that. In the case of Cyanotech, they're stressing a strain called Hematococcus to make astaxanthin. It's a valuable type of xanthan molecule. It's a pigment that can be fed to fish, for instance, like salmon that are grown in. They're normally fed like cornmeal or whitefish, and it won't produce the nice colored salmon. So by growing astaxanthin as a supplement, you don't have to dye the salmon to make it more palatable. You can just feed the astaxanthin supplement and have farm salmon, not deplete the resources as much. So that's a very valuable product, as well as some of the antioxidants you may have seen on the shelves that can also be produced by algae. In the case of Rice Farms, they also sell their spirulina as a protein source and as a nutraceutical, as nearly complete protein. But these are all more valuable products than fuel, which is extremely cheap at this time. But at the same time, it's at least a proof of concept that these strains can be grown in these types of systems in open ponds. These particular strains were selected not only for the production of these value-added products, but because they're robust in the open environment. In the case of spirulina, it grows at earthrise, they grow at an extremely alkaline pH. They grow at a pH of 10. So it's very difficult for many things to grow in there. A lot of people are proposing using strains of algae that can handle really high salinities, and that would be a selective mechanism that is non-hazardous, unlike herbicide-resistant corn. You would be able to use just salinity alone to try to keep other strains. Tubular photobioreactors are much less prone to contamination, but very expensive, and so they become cost prohibitive, and that's all I have to say about that. They are very productive. That one on the upper left is from Green Fuels, and it was one of the first algae companies to come out and say that they're going to make the most, be able to make a fuel, and it's going to only take a couple of years, and that was at least a few years ago. And so, I think that we have to be rationally optimistic about this technology, but I don't think there's anything prohibiting continuing forward at this time. Everything looks good.
How do you get CO2 when there's no air?
This was actually co-localized in New Mexico from a power plant. They just bubble it in from the bottom. So similar, people also use bag cultures, just really large polyethylene bags, and you can just inject a line with the bubblers and just bubble it in. But the main thing with these tubular photobioreactors that makes them really efficient is that you don't have as much shading as you might have in a pond, so you can control the light measurements. And there, especially in Europe, there's some examples. I believe this one on the left here is in Germany, and it's extremely efficient. You produce a lot. But if you're not producing a very valuable product, it's harder. And fuel is very cheap. So I'm more of an advocate of raceways that are strained that can handle raceways. So you've got much higher capital costs, operating costs. It's a little, but in open raceways, you're going to have evaporation and invasive species as two of the main things. And I guess the third one would be the possibility your species may invade the surrounding environment. So the estimated price per gallon is all over the map. This is also from NREL.
Is this one updated or is this last year?
This is last year. I haven't updated it since then. I don't think it's really changed much. Although there is, I actually was surprised to see Sapphire, talk by head of Sapphire, that was in the range of the original Benjamin predictions. Very inexpensive, in the $5 dollars per gallon estimate for their plant that they're building right now. So we'll have to. It remains to be seen whether they can pull that off. That'll be really interesting. But I'm not so concerned about this. There are some that are just really astronomical, $1,000 or $990 per gallon. But I'm not so concerned about $10 or $20 per gallon. I'd like to see it get down as soon as possible. But I wouldn't be surprised to see our fuel prices match what's already occurring in Europe, for instance.
Give it some time. Yeah, if you can do $10 now.
Exactly.
Care to touch on Solix there? I mean, they've got current rather, and then
Well,
initial production. I mean, I've been there a couple times, and I'm just curious if you had thoughts about their realistic approach towards getting to those low numbers, because they're literally.
Yeah, I know that they're actually collaborating directly with New Mexico State University and the Department of Energy to do some actual large-scale tests. So I would expect that they should have some real numbers that they should be able to present. And I know that they sell their reactor systems as well. So I think it's only a matter of time. It's kind of like good music or bad music. You know, like if the music's really terrible and you hear it on the radio, you won't hear it for very long. You might hear it and have to deal with it and change the station. But it's not like 20 years later, hopefully. You know, actually, I still do sometimes. But not as much. You're not going to hear that one hit wonder coming along. But I think there's going to be staying power for the ones that really are predicting something that makes sense.
So have you seen any biodiesel made from any of these companies from algae oil yet?
Yeah. Cool.
This exists.
So when you say biodiesel, all I've seen is bio-SPK or jet fuel or renewable diesel. I haven't seen anyone say that they actually made.
Yeah, it may not be, I should restate that, not
they're not
necessarily
saying
biodiesel. It may be renewable diesel or some other surrogate. But I'll tell you one thing though, is that all the analytical methods that currently are used to come up with these numbers are all production of biodiesel. But they're making methyl esters, they're extracting the oil, they're making methyl esters. So it's a Bly-Dyer extract, is the extraction procedure that's typically done. And they're esterifying, they're using an acid or a base, usually acid esterification, to actually produce the fames that they're running down either a gas chromatograph or a HPLC to get these different chromatograms that I've been showing. So I've definitely made biodiesel in the lab as a graduate student and tested it, but it wasn't like volumes that I can bring and show you. So I mean, we know it's there only because we're making biodiesel. That's the analytical technique for using the quantitative.
The ones that are being made in the lab, are they hitting the ASTM standards for biodiesel?
Oh no. So so we're making what we're doing is it's basically in a hexane solution or something like that. Right. So it's quantifiable, but it's not necessarily like. I guess we could dry down a hexane and get a small amount. We joked around about doing it, but it's never grown into that scale. Because what it really comes down to is at the point where you're really willing to invest in producing an acre's worth of a microorganism, you have to prove it in a vial first that it's even worthwhile, that it is better than what's already been done. People have done that. It's been reported. So if you're going to continue to get funding to do that kind of work at an academic or research institution, it needs to be something that's better than already been reported. So you have to be able to show it in a vial first. Yep.
What about microbial pathways needed with digesters with wastewater treatment plants? The other pathways extract. You have to have extraction, right? You have to have processing. What about growing the different kinds of microorganisms as part of a wastewater treatment plant? Normally, a wastewater treatment plant, you don't want things growing in your nutrient-rich water.
Right.
And the whole objective is to precipitate out the nutrients. But if you use the other approach, you need to be a much bigger wastewater treatment plant, for sure.
Well, there's someone from San Luis Obispo. I'm sorry, I can provide you information. Who's actually been doing those studies in collaboration with John Benneman, who's actually has some studies right here on the left side. to actually compare the comparable cost of traditional wastewater versus treatment where it's pre-treated in a Raceway. And they've actually got a strain, I believe it's a chlorella strain in San Luis Obispo, and they're using real wastewater and growing the chlorella first as a pre-treatment before putting it into post-treatment. And they've been able to decrease the amount of time that the water is actually in the traditional treatment plant. And what he proposed is that it's basically a similar cost after, because the amount of residence time that it's in the regular treatment plant is so low, you could have a smaller sized plant.
So follow-up, the cost of the plant is similar. How much more energy are you producing at that plant as opposed to just digesting the solid, not digesting the nutrient?
That's a good question, and he actually showed pictures of biomass that had been centrifuged out of the plant. I don't know the energy, I don't think there's been a life cycle analysis done at this point of how much energy went into centrifuging and how much comes out of it. But it's definitely interesting at this point that people are starting to make those connections. That was a native chlorella, by the way. It was just, he basically provided the pond, bubbled it with CO2, and then just let whatever grows naturally. It's kind of, there's another group that has been doing pyrolysis. I believe it's on the East Coast. They also presented at the same conference. And what they call the algae they grew is the crabgrass of their state. So it's just something that naturally falls in.
10 minutes.
Okay.
Where do you get your algae now? Where do you go find algae?
Texas.
I mean, seriously, you're going
If you put, you can find it anywhere. If we could go outside, I could probably, any soil sample, there's going to be algae there. And that's what a lot of these research efforts are doing, is basically going all over, sampling, and then analyzing the results of how much lipid, what's the productivity of that strain. And that's been a huge effort. So I'm finally getting to what the point of this whole talk was, the productivity estimates. So, a lot of people have also asked, just last night actually, someone asked about what's the productivity in nature, and I'm actually working on the Great Salt Lake study there. And it's interesting that in the Great Salt Lake, the estimated productivity, primarily driven by Dunaliella, a type of green algae, is about 145 grams per meter squared per year. So that's not really too much in terms of production. What we're looking at for cultivated algae, I think realistically, is 10 to 25 grams of dry weight per meter squared per day. And that's pretty amazing, because if you can imagine growing vegetables, I've seen zucchinis grow pretty fast. Like a zucchini in your backyard can just go giant out of nowhere, but you just don't see higher plants double every day. A corn plant go from 1 foot to 2 foot to 4 feet, and be 8 feet by the end of the week. It takes a summer, or 30 days at least, or 60 days. So the cultivated algae in open ponds that are available in nature, 2 to 3% solar energy conversion efficiency is considered normal. 1% conversion efficiency of light into energy is very strongly reported. That's totally undeniable. And that's compared to higher plants that you're looking at, 0.3% for the fuel that you're producing. So theoretical algal biomass productivity, if engineered or gone through breeding processes, we're looking at 8 to 10% solar energy conversion efficiencies, and production weights of up to 75 grams of dry weight per meter squared per day. So that's a pretty nice weight. But what I really wanted to get to in this talk is, what does that mean in terms of land use? How does that relate to what other people have said about land use? So again, agricultural plants, we're looking at 0.05% for some of the plants we really like. Like you're eating dates or olives or something like that. So maybe 0.3% for the best. That's sugar canes. So that's the DOE value for sugar can be 0.3%. And that should say max 1% for sugar cane. It's a faulty cut paste. So established oil productivity, so a percentage of that biomass, which is oil, is under stress, and algae can accumulate up to 80% or 90% lipid at really high levels. That's not normal. Maybe under nitrogen deprivation, a typical algae might get to 40 or 50%. But other algae accumulate high levels of lipid, and they grow very slowly. So you can't just take a lipid content per cell and then kind of mix different things like another cell's growth rate and say we're going to extrapolate this level of production. So what I've seen from these references here is a 50% oil content is considered a reasonable goal for continuous culture, not just at the end of growth, but as continuously being produced. You can't just measure oil content on Sunday and then multiply that by every day of the week. I think it's a little more reasonable to say maybe 10 to 30% oil content over continuous culture, but potentially getting up to 50 to 70% with proper genetic manipulation. So considering those things, in this particular study, the results for theoretical cases for different areas came out to around, it's hard to see, but 4,000 to 5,000 basic gallons per acre, or gallons per acre per year. So 4,000 to 5,000 gallons per acre per year. The original aquatic species program said 10,000 gallons per acre per year. But I've heard from authors of that actual report that it was embellished getting additional funding. And that's not what I'm here to do. I'm not here to sell something. I'm here to provide the information that I think is reasonable. And I wouldn't be interested. I'd be doing something else if I didn't think it was worthwhile. And so I'd want to know, as my advisor used to say in grad school, you can't get bad news fast enough. Might as well put our efforts into something that's useful. So what that really comes down to is if you can produce approximately 1 gallon per meter squared per year, and I'm back calculating now, that would be, so these numbers come out to about 1 gallon per meter squared per year, which comes out to about 3,465 grams per meter squared per year. And so that's about 10 grams per meter squared per day of oil. So you can figure that out. That means that 30% oil, that'd be 30 grams per meter squared per day of productivity, which is pretty reasonable from my own experience for the amount of algae that we can produce. So it's reasonable, okay, so around 4,000 to 5,000 gallons per acre per year. So how does that work out in terms of this bigger picture? So that comes out to, for that prediction of acres, that turned it into square miles, and that comes out to about 2.6 million gallons per square mile, not considering the space between, just as a rough approximation. These are rough numbers, I realize, but it's just to give an idea of economies of scale. According to, I looked up last night, and this may not be the only source, but 18.66 million barrels per day are produced or used of oil, and that works out for 42 U.S. gallons. Actually, I accidentally calculated this with the barrel size for beer the first time, and then caught myself, so I was really glad that I didn't do that. Because you guys would have been like, oh, I think that's not an oil barrel. But it comes out to 286.3 billion gallons of liquid fuel per year. That's for everything that we're using. That's gas, diesel, plastics, that's everything. That's all the liquid fuel that we're using. Ethanol, that's all of it. So the crude approximation for algae-based land use based on that would be 100, based on the number from the previous slide, would be 110,000 square miles required, which works out to about 333 by 333 miles. It's basically similar to the aquatic microbial phototroph model presented by Meuser et al. That I showed earlier. Is a reasonable, that was around the same thing, less than 500 by 500 square miles. And that's similar to the existing U.S. corn crop to meet 100% of the U.S. liquid fuel demand at that value of production, which is around 10 grams per day of oil and 30 grams of total biomass. So, however, I realize that this is not an adequate analysis. It's inadequate because we don't have commercial fuel from algae at this time, and we don't have these kinds of extensive life cycle analysis. Now, in the case of corn, we do have examples like this where people have looked at ethanol from corn. So with corn agriculture, you can produce about 400 gallons of ethanol per acre of corn. And it's estimated it takes 50 gallons of petroleum to grow that corn. So similar to that kind of analysis that I'm doing. You take into account transportation and conversion efficiencies, though, and there's kind of all over the map in terms of what's the carbon neutrality of corn-based ethanol is. And generally, it's generally held as positive, that it's energy positive. But it's been kind of debated at times whether corn ethanol alone is energy positive. And that's kind of rough when you consider that, it looks pretty straight ahead when you look at these straight numbers. 400 gallons, it only takes 50 gallons to grow. Where's all the rest of this, to run the center pivots, to make the petroleum. But there's a lot of these other things in transportation, conversion efficiencies. And so, take home is basically that we can do a lot with it, but I don't think that we have enough data at this time to tell you what the USR, what our daily allowance is going to be. This is also, so it's the final figure I'm going to show from this Nature. I know we're getting close to the end, but this is the final figure from this that I want to show from this new Nature paper from Stephen Chu. And this is the total energy usage in the United States. I really like to show the whole picture. And you can see that it's interesting over time, wood has really declined. You know, wood's not used very much. And this is interesting in relation to another graphic shown earlier, like labor and other and coal is also in decline. And actually, in terms of the oil usage since the 1970s, we're actually, you know, doing pretty well in terms of cutting our usage. I didn't realize that until I saw this. But renewables are a little tiny pink sliver right there. We've done so much to organize people and to create a community and develop the technology and stop using outboard motors in 55-gallon drums. And we're getting a lot, we're moving in the right direction, but we have a long ways to go. My thought is that I don't think we can do it with higher plants alone. And there's still a lot of, I think there's a lot of potential in algal biofuels. It's like the industry has matured. We've overcome some major political infrastructure barriers and communities have been created. We're starting to reach the saturation point of using plant oil and starch for biofuels, but we're still only matching a few percent of total transportation demand, maybe 5% of on-road diesel by 2012 or 2022, what people are talking about. Cellulosic ethanol is coming online at the moment, but only on a very large scale. So in terms of the grassroots movement for cellulosic ethanol, that doesn't seem like something that's going to be happening, but it could be part of the solution. In terms of these microbial phototroph feedstocks, we've done the extensive bioprospecting over the last 30 years. When we looked at a variety of natural phototrophs, I don't think that there's going to be a superstar that's going to come out of nature. I could be proven wrong, but I just think we've basically done the bioprospecting at this time. And we basically, the same common targets are coming up over and over again, the same types of strains. But in these rudimentary analysis that we've done in terms of productivity from light are very promising, especially in comparison to higher plants. We're talking about tens of fold better conversion of light into these products. But the technology is so new, this form of agriculture, the amount of energy it's going to take to separate it from water, still, I think, requires, we have to be modest about what it may take. I'm not willing to go out on a limb to say that it's absolutely going to be the case. But basically, the last thing is that I really feel that genetic engineering is going to need to be applied because we can again make another tenfold improvement beyond what's already available in nature. And I think we can do it sanely and safely and not in the face of public safety, but that is another separate issue. But even without that, without genetic engineering, I think that compared to other existing agricultural plants, there's a lot of promise. And unfortunately, we'll have to wait for a next talk or another talk to really get down to what I think is going to be, a reasonable amount. But the bottom line is that energy conservation is king, and that the less we can use, the more we have. And that's no matter what fuel source. It's always going to be more demand than there is supply. And then I think that because conservation is going to be the major source of growth at some point. There's going to be finite resources, and then conservation is going to be the form of economic growth. The less you use is the more you have. And that vascular plants alone are never going to be able to meet our current liquid fuel demand unless we seriously step back. And but there is clear feasibility to convert sunlight to liquid fuels since the plant 100% all of U.S. demand from microbial phototrophs. So I think the next steps, though, are to be use real-world data from the plants that are being, our company, the company I work for, is starting to build an 81-acre facility to start growing some of the strains that we have. And some of the other companies that are starting to grow strains. Look at this data from a complete life cycle analysis, being honest about the fertilizer, power demand, transportation losses that are required. And then, and see what we have at that point with and without the engineering. So that's all I have at this point.